Thank you, Mr. Chairman, for such a wonderful introduction, and also for inviting me to the workshop today. One of the key challenges with envelope tracking systems and these more complex, advanced modulating the supply type of systems is the signal processing required to make it play. And so my talk will focus in on the digital signal processing and the other signal processing techniques that are required to make the system work. And what some of the symptoms are when the signal processing needs to be modified somewhat. So I don't know that I need to spend much time on introducing envelope tracking. It's been pretty well covered earlier in the day. The key thing I want to highlight here, though, is that we are running the PA into compression with the envelope signal. So we are pushing it to the optimal efficiency points, and that typically is the trajectory that we use in the VN, VD space, or VE, depending on which terminology you want to use. The outline of my talk today, I'll start out by focusing in on the digital signal processing with the DSP, digital predistortion pieces for the RF chain. Now part of what we do with the digital signal, the DPD, is we predistort the envelope path as well as the RF path simultaneously. So that way we stay on the trajectory that we define for the relationship between the two. And I'll go into why that's important when we get further down it when we address the back-off conditions. One of the other pieces to this is making sure that the AM to AM or AM to PM that are used in a memoryless predistortion have a reduced bias associated with them. Many times when you extract a model, if you have measurement errors or modeling errors that creep in, that'll create a bias all the way through your DSP and DPD aspects of the whole system. So you have to make sure that your expected gain characteristics have the modeling errors and the measurement errors dialed out as much as possible to reduce those biases. I'll then talk a little bit about the dynamic supplies and envelope tracking blocks and what needs to happen in the whole system. Many people have already talked about that in this workshop, so I probably will go pretty fast through that. And then considerations for power control, which again is the back-off part. I'll then focus in on detroughing. I saw a little bit this afternoon on the detroughing. I don't know how much was covered this morning on that. I apologize. I was distracted, not really much. Okay, I'll talk a little bit about that. We'll then go into some of the waveform complications. I'm not going to get into all the waveform complications. As Professor Larson was just saying, our life is going to get more challenging moving forward. In addition to the bandwidths getting wider, designing a PA just for one particular bandwidth is, we're starting to see those days wane also. LTE is a case where at times we're going to have just a few RBs activated on one side of the band or maybe some on the other side, and then they'll come up with LTE-A, which lets them do RBs on either side of the band simultaneously. So if you thought life was starting to get challenging with the full boat of LTE waveforms, just wait until they start doing this to you, because it's much like having two modulated two tones running through and doing some interesting things with your third order intermodulation. So we'll have lots of challenges going forward. But anyway, I'll touch on some of the waveform complications, not necessarily that one, but some of the things that are happening in that regard to help alleviate that. And then some I/O subsample alignment questions. This is one place where you can get some of this modeling bias creeping in if you don't do subsample alignment between your input and output vectors. So I'll touch a little bit on that. And then finally, correcting for wide modulation bandwidths by making adjustments just to the envelope amplifier waveform and doing DPD in a two-dimensional surface. I'll touch on some of that, which is really ongoing research There's at least 3 groups that are researching that and publishing, and so I'll touch on that at the end. So digital predistortion for the RF chain. If I just have a standard PA and I want to add digital predistortion in, I'm not doing any envelope tracking, I'm not doing any supply modulation, I just wanted to add DPD. I'll start by just pointing out the standard PA and then what we need to add to it. So I'm going to say this is our typical PA. I mean, we sometimes have dual up conversion, and we sometimes have more complexity in the blocks here. But in general, we have some modem chip that puts together the bits and runs it to a DAC, and then we run through some up conversion chain into a PA, and we sample that output and feed it back. And this would be a closed loop type scenario. If we have an open loop scenario, well, this actually has no feedback yet, so this would be more for just power tracking. We would have something like this. If we add DPD to it, we would add in an AM to AM and AM to PM lookup table here before the DAC to allow us to modify the waveform before it got out to the RF chain. And then we would add some switching to the output here to allow us to have our feedback go back to help build the lookup table, or have the feedback path be driven by a particular source. Turns out these are called loopback structures, and South Cal often uses these kind of loopback structures to help speed up the calibration times. But the bottom line is you want to know what your receive path is on this side so that you can calibrate out any of the distortions that it's introducing. Because ultimately, if you have a clean waveform here at the ADC, that doesn't do you any good necessarily over here at the PA. That's really where you want the high quality signal, is out here at the output of the PA. So you need to, in essence, de-embed whatever this down conversion chain is doing on your feedback path. So if I look at memoryless predistortion for a class AB PA, we can talk about the output vector Y as having a gain which has some memory associated with it, which is why I have the underbar that includes the recent past of the input signal, times the input signal itself. So this is a form of describing the gain of the PA with some memory. The other thing we can do is look at the output signal as having 3 components to it. One being the memoryless component, which would be the expected value down the middle of the cloud here. There's also a memory term, which includes that recent past. And then there's a noise term, which is a random piece that's non-repeating. I really can't predict it. It could be jammer related, it could be spur related, it could be shot noise, it could be a number of different things that are undeterministic and random as far as a sample by sample basis. Now, this particular approach goes and it looks across the range of the input values, and it defines up different size bins to do the calculation for the expected value. And you might ask, well, why do I decide on different size bins? Averaging is averaging and it's all nice and clean. Well, if we look at the AM to PM, or if I flip the V in versus V out to gain versus V in, you can see that, well, there's 2 things that are going on here. One is the waveform has a probability distribution function to it. I don't have many points up here at the peak, and I don't have many points down here at the low end. But I have a lot of points in the middle. So I actually have this non-uniform sampling of the distribution, and that can create a modeling bias, which can actually ripple through the whole digital predistortion and ripple through the memory modeling, and a whole bunch of other issues can show up. So that's one thing. And if I tell my favorite statistician friend, I've got this problem where I have non-uniform samples in space, they're going to say, okay, well, do averages with a fixed number of samples, so it makes a non-uniform bin width. Well, that's great if I have uniform variance. But I don't have uniform variance. either. I've got wide variance down here at the low end and very tight variance up here at the top. And so even if I do the same sample count for each bin, my confidence interval for the estimated mean down here at the low end is still going to be very, very large. So I have to include more points down at the low end there to get the same confidence interval to my estimated mean. And that's what this is trying to say. It doesn't come through real clearly in the equation, but I figured I'd explain it verbally first. And I explained it in this curve a little bit more. I walked through all three of those scenarios. And the bottom line is I'm able to, at the end of doing the combining additional points to get the controlled confidence interval, well, there's a countering force to that, and that is when I have a trend in the amplifier behavior, the compression starts to happen, or in the previous slide, you can see that the AM to PM is starting to move at the low end here. Both of these are trends, and I need to actually reduce the number of samples that are used again to track that trend. So as long as there's no trend and everybody's in the same neighborhood, I can lump as many points as I want together. But when a trend starts to show up, I have to start trimming them back out again. So there's these counter-opposing forces of how many samples go in the averaging window when I do this. So I wind up with very, very small sample counts in the estimates up here at the high end because of the low variance, and then in the high changes that are occurring. Down here at the low end, it winds up being a moderately high count, but again, it's based on the trends that are occurring in the model itself. And so at that point, I'm able to extract out a compression characteristic that's built on a table of consistent confidence intervals over the whole operating range of the PA with this distribution. And my ultimate goal with digital predistortion is to land on this red dashed line on the middle. I'm able to directly create the predistortion table off of the measurement that has this filtered behavior, or I've filtered the behavior of the measurement and generated directly this compression characteristic here to do crest enhancement, in essence, on the signal that goes into the RFPA. And by building the exact crest enhancement to apply to the PA before it gets into the DAC, and then run that signal all the way through the RF chain, hits the PA, it goes through this compression, and it winds up on that red line in a very clean way, which we'll see in this slide. So I start out with my memory, my straight through measurement. I'll go ahead and I'll fold in my DPD block, and now I'll measure the system Q from this input over to here, and I get this nice straight line. Now, I did not linearize the PA itself. The PA is still just as nonlinear as it was before. I just modified the input waveform to compensate for the compression characteristics of the PA. Okay, so that's a bit of a subtlety there, but it's important to know that this curve, when you see it, it's actually a simplified block diagram of from way back in the digital part before you did the DPD to the output of the PA. And we have our linear gain component with the memoryless correction. I still have my memory term here, and I still have my random noise term. Now, one of the things that often happens in measurement scenarios is we play these signals in a repeated form over and over and over again. So we build these as a circular pattern. In the best cases, it's built directly off of a correctly generated modulated waveform. And in the same way we do averaging with the spectrum analyzer, I can use that repeated sequence and do averaging on it, and take each capture as an entry in an ensemble. And when I do that, I can identify changes that are deterministic to each sample point in the sequence. And again, it's the exact same thing as all the other averaging we do and so many other measurements that we do. And in that way, I'm able to eliminate the deterministic memory. Now, what this does is it gives me a lower bound of the memory that exists in the system that can be corrected. It doesn't build a model that I can use, in a deployed system, but it does give me an idea of how good the measurement system is and how good the component is and what that lower floor is for the memory modeling, which I probably won't spend much time on the memory modeling, but that is something that I've done a fair amount of work on, and typically we're able to get about half of that back without too much effort. It depends on the specifics of the PA and the specifics of the internal states of the PA that are creating the memory. So this is a general block diagram that you've probably seen in every presentation today so far. So I probably won't go into it in too much detail. One thing I do want to highlight is at UCSD, one of the things that we do is this digital IF, which eliminates our IQ imbalance issues. So most of the, let me rephrase that. All of the signal processing work we do here, I don't pay attention to IQ imbalance issues and LO leakage through the IQ modulator, because we're able to put that aside by sacrificing half of our bandwidth on our DAC and doing a digital IF or digital IF frequency and get away from that issue. The other thing is our envelope amplifier here. Most of my results will be based on a base station sized envelope amplifier, which has a peak capability of about 100 watts. It's typically supplying to the RFPA 60 to 80% of that, depending on how it's tuned up and the specifics of the waveform. And then the RFPA in general is running anywhere from 50 to 80% efficient. So depending on the specifics of the waveform, that's the general configuration of what we've been working with. The DPD, this shows how we've taken the DPD that I've talked about earlier and applied it to envelope tracking and how it's a little bit different. The first thing you'll notice is that the AM to AM curve from fixed VDD to envelope tracking is very different. As you noted earlier, as someone noted earlier today, you can pick a trajectory in the VD, VN space to have different features. I believe it was the gentleman from Skyworks was saying that he selected in one case a constant gain trajectory. Professor Larson conveyed an approach that we typically take at UCSD, which is optimal efficiency. And that's because we know we're going to implement DPD along with it. And as a result, what you wind up with is pretty much you get a linear relationship up here at the top. That actually has to do with the way the trajectory is set up, and I'll get to that in 2 slides. This particular PA is a switch mode PA, and so what you'll see here is a little, it looks like a paintbrush painting on the page. That curvature that goes up like that is a gain expansion. This happens to be a switch mode PA that the current tends to go to 0 when you turn it off, or at least very, very low values. And as a result, you get a lot of gain expansion down here at the low end. And when we do pre-distortion, earlier I was saying that you get crest enhancement with the constant VDD waveform. There's no crest enhancement with this one. It turns out the peak to average ratio actually goes down because of this gain expansion down at the bottom. So it's a very, it's a little bit counterintuitive. Now I also pointed out, I said that this isn't in compression. Well, that's not exactly true either. It's in compression from about a midpoint somewhere in here all the way up. It's everywhere it's 2 to 6 dB compressed, as Professor Larson was pointing out. So it's just that we're moving the VDD along with the VN simultaneously all the way through. And in that way, it's not showing a compression behavior, but the PA is in compression, and it is kicking up the third harmonic in that range in a much stronger way than it would normally. The other thing I wanted to point out on this slide, this happens to be a pretty narrow bandwidth signal, and it's using a very high fidelity envelope amplifier. You'll notice that and this is the same device, this has more capacitors tacked on the VDD supply line. But you'll notice that the RMS error between these two is reduced significantly. It's about a quarter in the envelope tracking mode as it was in the fixed VDD case. And that's because that the output supply voltage is being driven now. It's not, it isn't creating additional memory effect that's rippling through to the output. We're driving it in a high fidelity way, which actually reduced one of the memory effects that was contributing to the PA initially in the fixed VDD case. Now, having said that, this is the AM to PM, and again, we can see that we start out with quite different AM to PM in the two different cases, fixed VDD and envelope tracking VDD. But when we get to the memory effect remainder, you can see that the memory effect is actually a little bit larger and on the envelope tracking side. And that's part of the reason for that is that it's not any better because the RF signal is really the dominant effect of the AM to PM through the chain. But the other thing that kicks in is that the envelope signal will further modulate the AM to PM. It doesn't create an AM to PM directly, but it will modulate the AM to PM because of a couple times you've seen the surfaces, the performance surface of V out over V in and VD. Those surfaces, there's also a surface that goes with the AM to PM. And so when you start pulling on the VD, you'll get additional splatter on the AM to PM as a result of that. Now, if we're in backoff, this is some work that Joanna Yan and I did, and I'm still trying to find Joanna. I don't know where she went. She has got a couple pieces of paper that are important to me right now. One of the experiments that she and I did was we operated the envelope amplifier in full power, and then we said, okay, well, what happens when we back off? Well, you don't just back off on the RF signal alone. You actually have to modify both the RF signal and the supply line signal simultaneously to keep you on this same VD, VN trajectory. And that way I can keep using the same DBD table, and we get efficiency gains in backoff even, and so on. It kind of ripples through the whole system. And in this particular example, we started out at full power, and then we backed off by 3, 6, and 10 dB. And this shows the V in, V out behavior at each of those different backoff levels. And what we did, we noticed one of the issues I pointed out earlier with the compression characteristic modeling is if you don't use the right waveform, you get a bias that gets injected in. And so in order to get, if we model each one of these separately, we actually get a shift in the model all the way through because it's a different operating condition, it's a different dynamic equilibrium that the whole system is in. But if I use the full power signal and the 6 dB backed off signal to build the model, there's sufficient overlap between the two sets of data that one lookup table model has sufficient integrity to hold over that whole operating range from 10 dB backed off all the way up. And so this paper that she and I did really highlighted that fact and showed it in the lab actually working. So this is the one of these performance surfaces that I mentioned a moment ago. This particular one has I believe it was a gallium nitride on silicon. This region A is the saturated region. So if I pick a bias and I ramp up the input voltage, we can see this is the gain region here, then it saturates, and this is the saturated region over here in A. You might notice there's something funny down here where C is. Turns out this is in a switch mode kind of range, so there's a lot of gain expansion down there at the low levels. So we have a gain expansion region, a linear gain region, and a saturated region. This face is the saturated. And we often, a big part of what I've been doing at UCSD is working on building up surface models of this nature, which include the current as well as the output voltage modeling and the surfaces for it, so that we could predict the dissipated power, and then also look at the junction temperature and things like that. For the trajectory, this is a trajectory that we've often used at UCSD, this exponential form. And we tune it up such that the optimal efficiency circles wind up along this trajectory up here. And we typically clip it off at a low value here that still has sufficient gain that we don't have complete gain collapse and complete shutdown of the PA. The PA doesn't really like it to be taken down to 0 voltage, so we don't like to put it there. But I do like to have a smooth transition to that fixed value down there at the low end. And then the high end, we typically pick we set up this function so that we have a linear behavior up here. And it turns out the way that rolls into the whole system operation is that winds up being a constant gain contour by default. So we kind of fall into that same constant gain contour out in this range for operating. But we do wind up with more significant AM to PM. We're not really paying to AM to PM. We're going to take whatever the gain and whatever the AM to PM is along with this, because here we're trying to get the efficiency contours on this trajectory up here. That's the primary objective. So one of the key issues with all of these supply modulated systems is to figure out how to get the power supply variations to hit the junction in the middle of the RFPA at the same time the RF signal is getting there for that same operating point. And I'll start out by saying one of the symptoms of not having that lined up well, I'll back up to a V in versus V out plot. One of the symptoms of that is if this was ricocheting around in the corner down here. If we come down and it hits this axis, if it hits the x-axis at some value, ricochets up and hits the y-axis at some value and then comes shooting up again. That's a typical symptom of a misalignment between the V in and V out. Now, first we have to be able to do a clean alignment of that and do an estimate of how far those are off. That's kind of a first step. And the second step to that, well, first we want to be able to do that in the magnitude sense. And if I can do that in a magnitude sense and do subsample alignment, when I do that, I can also assess what the time delay is between the two, or between that, the input and the output vector. That number is actually quite important because I can also, in addition to doing it on the magnitude, I can do it on the phase, or equally well, the complex value. Now, why would I want to look at this number two different ways? Well, if we look at the functionality of the envelope amplifier, we know that the RF path is the only path that the phase is going through. The envelope signal only has a magnitude component to it. So when we look at the magnitude cross covariance and we're running the RFPA well into compression, that time alignment difference between the input and output is going to be dominated by the envelope path. When I look at the phase, or the complex form, that time alignment offset is going to be dominated by the RF path. And so if I look at the difference of those two numbers, that's how much they're off. That's the time difference between the envelope path getting to the active device and the RF signal getting to the active device. And I can use that delta T to then adjust on the envelope path over here the waveform, either move it forward in time or back in time a little bit to fine-tune that alignment and get all of these hitting simultaneously at the junction. Now, there's some complications to that calculation. I made it sound simple in the first slide. Now I'll dive into some of the issues that show up. And a lot of those issues happen with the phase down here at low values. When we talk about a modulated waveform, we can look at it in a polar form like we have on the left-hand side, or I can look at it in a IQ form over here. And when I'm going through the middle, I'm going to have a very, very rapid phase change as I go from one quadrant to the other, or from the first quadrant to the fourth. And if I have a time alignment mismatch between here as I'm shooting through the middle, it's going to be a pretty big problem. And this is one of the big issues with actually having the VDD value go all the way to 0. We want to set that to a small value so at least we're not aggravating that this transition through low values. So this is a quick sketch of one of the challenges with EER, having to go through 0. Some of the work that was done on this was with Fei-Peng Wang and Professor Larson a few years ago, and I think you might have been involved in some of that with Jeremy. The next step was to then go through and do look at with the phase cross covariance, make sure that we do that in a mathematical domain that makes sense. We want to make sure that we're using modulo 2 pi math on this, and we're not wrapping around the breakpoint in that numerical system. The other thing that's an issue when you look at the phase is that there's a very sharp cross covariance. That is a bit of a problem in that if I want to use a cubic spline, for example, to predict where the off zeroed point is, the cross covariance of a phase signal is actually more of a delta. And so a simple cubic spline doesn't model that very well. So we need to go through and adapt this in multiple time steps or multiple iterations as we fine-tune it in. That's the bad news. It isn't just one number, boom, there it is, you plug it in and that's it. You have to do it multiple iterations and kind of walk your way into the solution. That's the bad news. The good news is once you have it in, it typically doesn't move unless you have FIR filter, or unless you have SAW filters and you're changing temperature a lot or something like that, or you're changing cables all the time. But if you keep the cabling the same and you don't have a lot of temperature varying components, it stays stationary. And this is a block diagram of the computation. Essentially, you have a rectangular, you have Cortex here to build the amplitude and phase signals. You do the phase correlation and the amplitude correlation, find your deltas, find your maximum, and then do the difference to see what your delta is in time. And this goes into some of the issues with correlating phase. If I get a good correlation, I'll get a cluster of phasing like this. If I have poor correlation, it'll be it'll spread out much more quickly than the magnitude will. And again, this is because of the nature of the phase going through 360 quite often. And the other thing is where you pick your breakpoint. If you pick it to be around 0, then you keep everybody in one area, especially if you're going minus pi to pi. If you're doing a minus pi to pi and you happen to have your breakpoint around pi, your average will wind up 0, but you really have everybody lumped on either end, and it's not a very good distribution to work with. So, so there's some challenges with working with the phase cross covariance. But another interesting feature to this, and this is some work that Fei-Peng Wang did, you can actually monitor just about any one of your metrics, EVM, ACLR, normalized RMS error, and so on, and vary this time delay, and actually see the bottom of the bowl. You can watch it converge down to a minimum EVM and then come back up. So and I think in many polar systems, this feature or this symptom of misalignment is actually used as a mechanism to do the time alignment because you don't have as much control on the amplitude of the RF signal. But so this is a particular feature that's very, very helpful in confirming that you have found the optimal time alignment. And the other thing to point out on this is, and this leads to the observation that I made earlier of you can't just grab the number that it gives you, plug it in, and you're done. It's done. It's not a smooth linear relationship for the time delay and its projection as far as how far off it is. It has this kind of a wiggle form to it. And as a result, your estimates in one region may overshoot you or undershoot you from your target location that you need to land in eventually. And as a result, this is another reason why you need to iterate on this to tune it in to the correct value. So when we add in envelope tracking and DPD to a system, some of the other blocks that now need to be added are the lookup table or function that defines the envelope signal from the IQ, the complex IQ signal. So this again would be, we actually, on this side, we actually have a CORDIC to go into phase, magnitude phase space. We'll use that to do the, build the table that builds the envelope signal. And then we'll have a CORDIC on this side to come back to IQ to run into the up conversion chain and out. Here we'll also have a delay filter that allow us to do the subsample shifting forward or backward in time. Well, it's all one way because the RF path is slower than the envelope path. So this will have an integer delay and then some subsample delays that you can fine tune in. You'll have some phase signal amplitude control. This is in the idea of taking an EER system and making it an ET system. And then you'll have your delay mismatches also for the AM to AM and AM to, for the AM to PM delay. So if you are going to use this kind of a phase signal amplitude control, you'll need a block that goes with it. So for wide modulation bandwidths, this is where some of the more exotic DPD schemes are kicking in at this point in time. And that is when I don't follow this one-to-one relationship between the VD and the VN. If for the sake of the envelope amplifier, I'm reducing the slew rate or reducing the bandwidth, modifying that envelope signal, I may want to do that to help the bandwidth or performance of the envelope amplifier. But I still have to make up for that somehow and get linear behavior out of the output of the PA. And when I do that, we pretty much have determined that you don't want to be on the wrong side of the blue line here. If you get on this side of the blue line, essentially you'll need infinite RF input power to get to where you need to be for the output, and so you'll get extremely high peak to average ratios, and it just is not healthy for the RF chain. If we can do a nonlinear filter process that keeps us to the left of the VN-VD behavior, that allows us to essentially, when a point needs to be moved for the bandwidth of the envelope amplifier, we'll move it up initially, and then we'll adjust the RF signal once we've pulled that trough up. And this is one of the things that Joanna has been working on at UCSD, is this idea of adaptive detroughing. And so if I have a fixed envelope signal, our original might be, if I look at my original envelope signal, the square root of I squared plus Q squared, I'll have the black line here. If we do that fixed detroughing, part of its functionality was to reduce the bandwidth. I didn't actually state that up front, but that's one of its features, is I smooth out those spiky zero crossings. So that's the blue line here. So it reduced the bandwidth a little further. If I do adaptive detroughing and pull those troughs up on an as-needed basis to reduce the slew rate, I then reduce the bandwidth a little bit more. But more importantly, I've changed the slew rate operation of the envelope amplifier. And then what we need to do is modify the RF signal to make up for the changes in these red gaps that have been created to get us a clean performance. And so one way to do that is build this surface model. The one I showed earlier was built off of a harmonic balance simulation. This particular one is built off of 4 trajectories. We intentionally selected multiple trajectories to curve fit surface to, and then from that generate this kind of performance compression surface characteristic, or V in, V out characteristic. One of the things I had to do to prevent overfitting, though, is penalize for non-monotonicity. In other words, if I just escalated the order on these high enough, I could hit these lines exactly right, but I'd be all over the place in the curve. It would not be a nice, smooth, monotonic surface. And so by penalizing the monotonicity, or I should say penalizing the non-monotonicity, I was able to generate this surface off of these few trajectories in a very efficient way. And to kind of wrap things up, I wanted to give a few numbers to the performance that we're getting on the envelope tracking PAs at UCSD. The first couple are handset-sized envelope tracking PAs. And this isn't just the RF PA, it's the RF PA and the envelope modulator. So it's the total envelope tracking efficiency. Some of them to point out, highlight, 6 dB peak to average ratio, 50% efficiency with a 10 megahertz bandwidth. This is CMOS on CMOS with silicon on sapphire. 50%, again, 50% efficiency. Another one that's of particular interest is 20 megahertz wide. This is using the dual switcher that, I think both of these were using the dual switcher that Professor Larson was just talking about in the previous session. The rest of these are all base station sized envelope amplifiers and PAs, ranging from 5 megahertz modulation bandwidth up to 10. We have been pushing out to 20, but the particular envelope modulator that we've got, it starts to have some issues out there. So we're still working on the surface modeling to properly predistort as it's pushing out to those limits and limit the slew rate effects. But again, some of the numbers that are particularly interesting are 70% efficiency with the 780 megahertz base station PA with the WCDMA signal. On the one end, we've actually applied it even to millimeter wave, but one of the issues with the millimeter wave and some of the other specialized cases that we've done is we didn't resize the supply modulator to that particular application. And without resizing the supply modulator to that particular target output power, the numbers don't look quite as impressive. But we realized that if we were to redesign the envelope amplifier for that size, that they'd be the RFPA is operating very efficient, and there is a very nice solution space there. So being able to do these on the fly for the different sizes would be phenomenal. So anyway, last slide I have is a quick summary. I've covered digital predistortion for the RF chain, which includes, I've started with just a straight RF chain, but then I've extended it to envelope tracking. I've highlighted some of the effects of envelope tracking and some of the specific signal processing needs with ET systems, specifically the time alignment. And then I've also expanded the modeling that's required for a supply modulator that is unconstrained, I'll say, from the RF signal, in that it has a much wider range of operating points that it could be for any particular input voltage. So they expanded VN, VE access for the RFPA and what that means for the digital signal processing that's required. Thank you for your attention.
I have a question. Why focus just on the AM to AM? You know, when you start in, it looks to me as though you kind of you look at AM to AM, and then you take what you get on AM to PM.
No. Actually, if I left that impression, I'm sorry I did, because I typically look at the memoryless predistortion as a complex, in its complex form. I don't look at it as AM to AM and AM to PM when I do the modeling. I actually look at it as a complex gain. So all my coefficients in my polynomial are complex. So if I left the impression that I'm only looking at AM to AM at the beginning, I apologize for that, because it's very important to look at both the AM to AM on slide 11 and the AM to PM on slide 12. I look at this very in a complex space. In fact, typically I look at the gain in the complex IQ space, which is a strange way to look at it because most people don't even imagine it that way.
Right.
And it turns out you can see this splatter much more effectively when you put it into that complex space. The points up at a compression are all clustered around a small area, and the same number of points down at the low end are this huge area on that complex gain plane. And you really can see the way this wrong pointer, the way this dispersion down at the low end, how that affects that estimate of the gain. You can see it very clearly in that presentation form. So yeah, you
Right.
have to look at it as a complex number.
So another question, if I might?
Sure,
Is there
it looks
time?
like there's another question.
there's another
though,
question?
I think. Go ahead, Tom.
I think there's discussion about ACLR efficiency and EVM, right? I mean, meaning those are your targets, right?
Mm-hmm.
So shouldn't you be going after all of them all at once rather than just like efficiency first? EVM seems to be getting left out of the equation in some of
Yeah.
the talks I've heard. It's sort of like an afterthought. Let's check to see how bad the EVM is, which is sort of like, hey, you're trying to get a signal
Yeah.
across. And when it comes to real link budgets, right, maybe just meeting the spec is, you can't pass certification, but maybe it's not where you want to operate.
Yeah, typically, putting my other hat on for a moment, all of this work has been UCSD work. I'll flip my hat around to the Qualcomm hat for a second. You don't want to have it right there at the edge. I can't ever deliver something right on the edge of the spec compliant. I've got to have minimum 3 dB margin, maybe better 5 dB. People
For
are freaking
EVM?
out people freak out if I'm not, if I don't give them 5 dB margin on that. So to answer your question, I focus primarily on the efficiency because I know I have DPD working with me, and I'm monitoring how much I can recover with the memoryless DPD as I go all the way through this to make sure I have that margin.
Okay.
Now I'm back to my UCSD hat, by the way. If I can't recover enough with the memoryless, then I'll add the memory in. Again, with my PhD thesis and papers involved. 9 times out of 10 in production and in the industry, what'll happen is the RFPA designer will get beat up until it has sufficient memoryless behavior.
I see.
The DPD will work as long as it's consistent and repeatable and not changing. If things start to change and become chaotic, you're not going to be able to correct for it with memoryless or even memory corrections. It has to be consistent. And if you have it consistent, you can correct it out. And so that's part of the duality of this thing. If we're going to do ET, it better be consistent enough that we can do the DPD and pull the rabbit out of the hat, and we're going to go for the best efficiency. And if that first assumption isn't correct, well, then we need to make sure we fix whatever made that first assumption not work, and then come back to optimal efficiency.
So quick summary is target 3 to 5 dB margin on EVM
And ACLR.
and ACLR.
Yeah.
Was I
Actually,
wrong?
EVM, it depends on which standard you're at also. I'm talking CDMA when I do that, when I said those numbers. LTE has a different dynamic between the ACLR. ACLR is actually harder with LTE, as Earl pointed out, and some of that can be in the construction of the waveform. Some of that can be in other facets. But each standard
part
has
of
its
the
own
link budget,
trade-off
isn't
between
it?
the two.
It's still part of the link budget, right?
Oh yeah, absolutely,
For
absolutely. You
being
have
able
to
to
pay
receive
attention
a
to both.
symbol on the other end, right? So,
Yep.
so
You have to pay attention to all three of these things.
okay. So your comment about 3 to 5 dB was ACLR, really?
ACLR primarily, yes,
Okay.
with CDMA.
Thanks.
Yep. But you're right, you do have to pay attention to all three. Yes.
Yeah, early on today, we see presentations from RFMD and Skyworks, and their approach is mainly using ET without considering DPD. And in your presentation, DPD came into the picture. And my question is, using DPD, would that help you to improve efficiency? If it does, how much?
I can't really comment on what was said earlier about not operating with DPD. And my main focus on this at UCSD has been behavioral modeling of the system and generating DPD for envelope tracking. So I haven't really looked at that question, so I'm sorry.
But okay, when you, let's say, when you get the amplifier, I guess it's not Qualcomm amplifier, right? You get the amplifier from somebody else.
I only work with, all of the PAs here have been Nitronics, big LDMOS base station PAs kind of thing, you know, NXP.
But you do have results for handset PAs.
Yeah, that's some work that was done under Larry Larson, and that was like a Peregrine Silicon on Sapphire and a Skyworks PA.
Okay, those PAs are
And we did DP.
compliant with the 3GPP standard to start with?
Yeah.
Oh,
Yeah.
Okay.
So I can't comment on your question. I don't know. I haven't looked at that.
all right, thank you.
Yeah, sorry. Yeah, very good question, but I can't comment on it.
I got a question related to your equation. You basically are presenting the V out as a function of the V in. And then you have the gain, basically the relationship. So I understand it's a complex relationship that you are building up. But what's the reference impedance actually for your voltage out definition? The reason I'm asking is I'm wondering how sensitive basically the timing of the envelope is going to be related to creating mismatches at the output of the amplifier, or is that not of a concern?
Yeah, those are all concerns. How much time do I have, Don?
You have plenty of time.
Oh, okay. Because there's some very interesting things that happen. I'm going to go back to one of the earlier slides that I had where I have my general multi-box form right here. So when you talk about loading impact, there's actually multiple loading impacts that are occurring. What I've drawn here is the V out versus V in and VD. Okay, so when you have a load impact change on the output of the PA, what that's going to do typically is shift the gain, which is this surface. It'll expand this surface out. And it also impacts the gain expansion right there before it goes into compression. That's typically the next piece. And that's a ridge line just on this side of the interface of these two planes. Okay. And the third, and these are in priority level. The third one that'll have an impact on is the saturated voltage, the saturated output power. Actually, you could argue that that might be the second one, and the gain expansion is the third one. But that'll modulate this plane. Okay, so you're going to have this surface breathing, as it were, or undulating as you pull on the output load of the RFPA. Okay, now, if that wasn't enough for you, here's the next one. The current here, if this is a switch mode PA, will go to 0 down here where we're in this C region here, which means the load that the supply modulator is presenting is also getting pulled, not necessarily by the load pull that's happening over here, but more just the natural behavior of the RFPA. And so you're getting multiple dynamic loading events that are going on simultaneously here.
Is this,
Anyway,
is
it's
this,
very
is this
interesting
like
space.
an average approach then here, or are you saying this is an approach that's working within a certain impedance environment, or?
So I primarily work within the environment of a base station PA. The nice thing about base station PAs is that most often they have circulators on the output. So we don't have to worry about the breathing surface from the load modulation side. It turns out thermally it still does that. This quasi-static surface here was originally generated via harmonic balance. When we do the individual trajectories, we can actually see the trajectories get close to one another, but they don't necessarily intersect. So they set up a dynamic equilibrium that's slightly different, that has a slightly different gain in this low power region or a slightly different saturated power up here in this region. So the challenge with doing the multiple trajectories to build the surface is that you have to figure out how to reconcile those non-intersecting but similar surface behaviors.
Okay.
So it's still a big challenge in dynamic modeling to figure this out.
Okay.
Yeah. But
Okay,
good
thank-
questions, Mark.
Thank you.